In example 6, we used substitution to solve that system. Now in example 7, we'll look at using elimination. Still identifying our two equations as 1 and 2. If we take equation 2 and multiply both sides by 2, we'll end up being able to eliminate one of our variables. Equation 1 will remain unchanged. And we can go ahead and subtract 3 over to the other side just to get these two equations in the same form. Equation 2 will become 2 over x squared plus 2 over y squared is equal to 10. From there, we'll add those two equations together. The negative 2 over y squared will cancel with positive 2 over y squared, leaving us with 7 over x squared is equal to 7. We'll multiply both sides by that common denominator of x squared to get 7 is equal to 7x squared, or x squared is equal to 1. Taking the square root of both sides then will give us x is equal to either plus or minus 1. So we have two different values for x. Now we'll need to plug those values back in to solve for y. So we'll turn to equation 2. If we plug in 1 over 1 squared plus 1 over y squared is equal to 5. 1 over 1 squared will just be 1, meaning we'll have 1 over y squared is equal to 4. Taking the reciprocal of both sides will give us y squared is equal to 1/4. Meaning, if we take the square root of both sides, y is equal to either plus or minus 1/2. So for that single x value, we get two different possible y values. If we next plug in x is equal to negative 1 into equation 2, we get 1 over negative 1 squared, which is still just 1. So our logic for solving this will follow the exact same path, and we'll end up again with y is equal to plus or minus 1/2. Leading us to 4 solutions in this case. The first being the coordinate pair 1, 1/2, and then also 1, negative 1/2. Then when we plugged in negative 1, we were also able to get two different values for y, positive 1/2 and negative 1/2. So 4 different coordinate pairs that represent those xy solutions to our given system. In example 8, we'll again look at applying the elimination method. In this case, multiplying both sides, every term on both sides of equation 1 by negative 5 will give us negative 5 over x to the 4th minus 10 over y to the 4th is equal to negative 25. And our second equation will remain unchanged. Adding those two resulting equations together, our terms with the x variable will cancel out, leaving us with 4 over y to the 4th. Not 4, sorry. We would end up with negative 16 over y to the 4th is equal to 8. We would multiply both sides by that common denominator of y to the 4th, which would give us negative 16 is equal to 8y to the 4th, or y to the 4th is equal to negative 2. What we have now is a variable being raised to an even power. That value always has to be non-negative. So in this case, we're going to end up with no real solutions, because there's no real number that we can plug into y to the 4th power and generate a negative result.